Welcome to Fawad's Deep Blue. This is the last great wilderness on Earth, a world of pressure, darkness, and ancient rhythm. Today, we descend. We're diving into freezing, pitch-black waters where evolution has basically gone completely off the rails, literally flipping the rules of biology upside down. We are going to be demystifying polar gigantism and looking closely at the frozen giants of the Antarctic deep. So let's jump right in and explore a phenomenon that's going to force us to rethink everything we know about how extreme environments shape life on our planet.
So ask yourself this, why on earth does extreme cold create giants? It causes some real cognitive dissonance, doesn't it? I mean, normally we think of extreme cold and barren, resource-poor environments as places that stunt growth. Think of the harsh tundra or high mountain peaks where life just kind of clings on in these tiny, miniature forms, conserving every single ounce of energy just to survive. You'd totally expect the freezing waters of the Antarctic to produce tiny, highly efficient scavengers, but the exact opposite happens. This harsh, freezing environment actually produces massive, oversized creatures. It takes small things and makes them big, and takes big things and makes them absolutely huge.
To really wrap our heads around the sheer scale we're talking about, let's look at sea spiders. A typical sea spider you'd find hanging out in a warm, tropical coral reef is about the size of your thumbnail, maybe 1 to 2 centimeters across. Tiny, right? But its Antarctic cousin, which belongs to the exact same taxonomic family, has a leg span of over 70 centimeters. Guys, that is wider than a dinner plate. Just picture a spider with a leg span longer than a medium-sized dog creeping across the dark seafloor on these massive stilt-like legs. Yeah, literal nightmare fuel, but also incredibly fascinating.
And it's definitely not just the spiders. This wild biological rule applies across the board down in the Southern Ocean. Take the colossal squid, weighing in at a staggering 495 kilograms. What's crazy here is that the colossal squid is actually a type of glass squid. That's a family usually known for being small and totally translucent, so they can hide in the water column. But in the near-freezing Antarctic, being see-through isn't really that useful. So it traded in its glassy camouflage for incredibly thick, insulating flesh with this reddish hue. That red color actually absorbs the light of bioluminescent prey, making it the ultimate stealthy giant. Oh, and then you have the volcano sponge, a massive sponge with a glass-like skeleton that grows up to 2 meters tall and over 1 meter wide. It's like an underwater skyscraper.
Okay, so the absolutely crucial point here is understanding exactly why this happens. The leading scientific explanation for all of this is called polar gigantism, and it's driven by something called the oxygen temperature hypothesis. Formulated by researchers Gautier Chappelle and Lloyd Peck, this theory basically says that for cold-blooded animals, or ectotherms, their maximum potential body size is dictated by a strict balancing act. It's the environmental supply of oxygen versus the animal's own metabolic demand for it. In the near-freezing polar seas, this balance tips unbelievably far in favor of gigantic growth. Let's actually look at the data to prove it. What's truly mind-blowing is the sheer volume of data backing this up. Chappelle and Peck didn't just take a wild guess. They rigorously analyzed the lengths of 1,853 different species of benthic amphipods. Those are small crustacean scavengers from 12 different sites all over the world. And the adult size distribution clearly proves that as water temperatures drop and oxygen levels increase, the maximum potential size of these creatures goes up curvilinearly. Basically, oxygen acts as a biological ceiling. In warmer waters, that ceiling is super low. But in the freezing Antarctic, the ceiling is pushed dramatically higher. This proves it's a hard rule of the ecosystem, not just a couple of weird outliers.
Let's geek out on the physical chemistry for a second to see how this works. It all comes down to a really simple rule. Cold liquids hold more dissolved gas than warm liquids. Picture a tropical ocean sitting at a nice, balmy 30 degrees Celsius. In that water, you have about 190 micromoles of dissolved oxygen per kilogram of water. But if you drop that temperature down to near freezing, 0 degrees Celsius, that oxygen concentration absolutely spikes to almost 348 micromoles. That means polar waters hold about 1.8 times more dissolved oxygen than warm tropical seas. The water is literally saturated with the exact fuel these animals need to power massive bodies. But hey, oxygen supply is only half the equation, right? The other half is demand. And this brings us to what biologists call the live slow, grow huge strategy. Because the water is so incredibly cold, the metabolism of these cold-blooded creatures slows to an absolute crawl. We're talking biological slow motion. And because their metabolic engine is running at just a fraction of the speed of their tropical relatives, their demand for oxygen just plummets. Maintaining a massive body suddenly becomes incredibly cheap energetically. They can afford to carry all that extra bulk because they're barely spending any energy just to exist.
Now, you might be wondering, when you get this big, how on earth do you move all that oxygen around a massive body, especially if you don't even have a complex respiratory system? Well, researchers at the University of Hawaii made a stunning discovery about those dinner plate-sized sea spiders we talked about earlier. As biologist John Harrison put it perfectly, sea spiders use their legs like gills and their guts like hearts. I mean, wow, this is a total paradigm flip in our understanding of animal anatomy.
Let's break down exactly how extreme this anatomy gets. Pycnogonids, or sea spiders, don't have gills. They don't have lungs. Instead, oxygen diffuses directly from the water through microscopic pores in their outer shell, or cuticle, right into their oversized legs. And beautifully, as they grow into these giants, their cuticle actually becomes more porous to compensate for their massive size. Scientists call this biological trick ontogenetic symmorphosis. And it gets wilder. Because their actual hearts are incredibly weak, they rely on peristaltic contractions of their gut walls, which by the way extend all the way down to the tips of their legs, to pump digested food and dissolved oxygen throughout their massive bodies. They are literally breathing through their skin and pumping blood with their intestines.
And this live slow strategy isn't just about size, it's heavily about time. Check out this number, 15,000. That is the upper estimate in years for the maximum lifespan of the giant volcano sponge we looked at earlier. Now, while some recent studies suggest their lifespans might be capped by geological ice ages to merely several decades or millennia, the mind-blowing fact remains that these organisms live in such extreme slow motion that scientists observing caught specimens over a 10-year period recorded absolutely zero detectable growth. Nothing. They are literally living on a completely different timescale than we are.
So why does all of this matter to you, and what's the big takeaway here? Well, it's absolutely crucial to understand that these giants are the product of a perfectly stable, incredibly slow-paced environment. The Antarctic Ocean hasn't just been freezing cold, it has been thermally stable for tens of millions of years. Temperatures barely fluctuate more than 1.5 degrees year-round. On top of that, there's a historic lack of shell-crushing predators down there, like large crabs. There is simply nothing forcing these animals to be small, fast, and evasive. They are perfectly, beautifully adapted to a highly specific, very fragile extreme. Which brings us, unfortunately, to an inescapable vice. The very biological rules that allowed these incredible creatures to become giants are now turning against them. Climate change represents a massive existential threat, acting as a deadly double bind for creatures that have evolved to live at the absolute limits of their physiology. For millions of years, they traded adaptability for sheer size, and now the rules of the game are changing way faster than they can possibly evolve.
Let's walk through how this trap closes step by step. Step 1, as the oceans warm, the physical chemistry we talked about reverses. Warmer water holds less oxygen, meaning the supply these giants desperately need begins to plummet. Step 2, as the water warms, the metabolism of these cold-blooded creatures naturally speeds up, meaning their demand for oxygen spikes at the exact moment the supply is dropping. They essentially begin to suffocate in their own oversized bodies. And step 3, those warming waters remove the thermal barrier that kept predators away, allowing heavily armored, shell-crushing king crabs to march right down into the Antarctic shelf. These are cascading dangers, plain and simple. We're looking at potential localized extinctions because these animals cannot quickly adapt to a multi-front assault. They are facing suffocation from their own rising metabolisms. The historic absence of predators is over, and because they've lived in isolation for so long, these slow-moving giants have literally zero evolutionary defenses against fast, aggressive king crabs. Add ocean acidification to the mix, which impairs the ability of sponges and mollusks to build their calcium and silica structures, and the perfectly balanced ecosystem of the polar giant starts to totally unravel before our eyes. So, I want to leave you with this final provocative thought. What else might we lose from the deep before we even fully understand it? The ocean covers 70% of our planet, yet we know less about its deepest points than we do about the surface of the moon. Fawad's deep blue is a reminder that the greatest mysteries aren't in space, but right here, beneath the waves.
These frozen giants are living relics of a stable, ancient world, and it really makes you wonder how many more incredible biological secrets are hiding in the dark. If this glimpse into the abyss moved you, please like, share, and subscribe to Fawad's Deep Blue, and let us know in the comments, what is the one sea creature you would most like to see in full detail? Keep asking questions, keep exploring, and thank you for joining me on this explainer today.